Next is the derived data type. To refresh the hierarchy of what we learned so far, let's revisit the vocabulary and grammar chart. It had the character set, which comprised of letters, digits, white spaces, and special characters. Then we learned about the tokens. Tokens are words derived from the character sets and are like building blocks of the C++ programming language. In tokens, we covered identifiers and keywords. Now we are into the data types. Starting with the data type classification chart, we first learned about primitive data types. Then the user-defined data types. And now we will be learning about the third major classification, the derived data type. So let's start with the derived data type. They are made up of multiple primitive data types. Hence they are extensions of the primitive data types. The derived data type includes arrays, functions, and pointers. The array. Array is a collection of consecutive memory units that store same data type values. An array is identified by a common name. And the individual memory units are referred to or addressed by their index number. For example, int a within square brackets 5 is an array of integers named a. It can store 5 integer values at contiguous memory locations. They are indexed as a0, meaning 0 index of a. Then we have a1, a2, a3, and a4. Each blank panel represents an integer element of the array. These elements are numbered from 0 to 4. Because in arrays, the first index always starts from 0. Since this example is an integer array, each array index can be occupied by integers like this. The next derived data type that we will be learning is about functions. The function is a predefined block of reusable program code that provides solution to a specific task. Functions are invoked by programs and can be reused by one or many programs. Functions can be written within a program or in a separate file. For a quick look, I have written the code for a function named prod, which when called by a program, executes the task of multiplying two numbers. A program will have to send the two integer numbers called parameters to the function for being multiplied. For example, a program would call the prod function like this. Prod. Within round brackets, 15, 10. Here, 15 and 10 are passed to the function named prod. The numbers get multiplied with each other, and the product 150 is returned back to the calling program. This is the function named prod that multiplies two numbers and returns the result. The function receives two integer numbers with names a, b here. The multiplication is done here. The multiplied result is returned back to calling program from this line. I am now going to demonstrate how the function works. Suppose there is a bigger program with several functions. This program needs to find the product of two numbers at some point within it. Then this program will invoke the prod function that we just wrote, along with the two parameter values, 15 and 10. Program control then shifts to the function named prod. Remember that a function can be written within the same program file, or within other external files. The first parameter 15 is passed from the main program to the first parameter location at a in the function. The second parameter 10 is passed from the main program to the second parameter location at b in the function. 15 and 10 are assigned to a and b respectively, and the product is obtained. This product is then assigned to m. Remember that m is a variable or memory location where integer value can be stored. We then have this return statement in the function, which means that the value in variable m has to be returned to the program from where the prod function was called. So the program that called the prod function now gets back the processed result. This is how the function operates. We will next have a look at the third derived data type, pointers. The pointer stores memory address of variables. It occupies 4 or 8 bytes of memory. As the name implies, pointers directly point to the exact memory location where certain values are stored. Pointers are used to allocate and deallocate memory during program execution. Hence a pointer executes programs faster and more efficiently. Let's have a look at an example of how and why a pointer is used. Int, asterisk or star symbol, PTR. Here, we declare that PTR is a pointer to the memory address of any integer. PTR carries the memory address, and star PTR points to the value within it. Int a equals 10. We then store value 10 into the variable named a. PTR equals ampersand a. We next store the memory address of variable a to the pointer named PTR through address reference operator ampersand. Cout a. Now we print the value stored in variable a prints 10. Because a is assigned the value 10. Cout star PTR. We next print the value stored in memory location where PTR is pointing to. This also prints 10. Because PTR points to the memory address where variable a is located. Now let's see from the example how a pointer makes program execution faster. In the example, we have two print statements to display the value of variable named a. The first is cout a, where the value is displayed by referring to variable named a. The second is cout star PTR. Here the value is displayed by pointing directly to the memory address of variable named a. So how does the pointer make program execution faster? Let's first see how the display command, cout a, works. When the command cout a is executed by the program compiler, the compiler usually requests the operating system to find the address of variable named a. It then fetches the value from that memory address back to the compiler, which is then printed onto the computer screen or the monitor. Let's next see how the cout works with the pointer command. When the command cout star PTR is executed by the program compiler, the compiler doesn't have to request the operating system to find the address of variable a. Since PTR already holds the memory address of variable a, the value of a is directly fetched from the memory location by the star PTR command, and is then displayed onto the computer screen. Hence the need to fetch address of variables from the operating system is avoided when we use the pointers. Let's now move to the last of the tokens. Symbolic constants. Symbolic constant is a label that gives explanatory name to any constant value. The value assigned to symbolic representations remain fixed throughout a program. It almost cannot be changed within the scope of execution of a program. Preprocessor directive, #define pi 3.1415, that we learned in the earlier chapter to define pi, is a symbolic constant. Symbolic constants can be declared by any of the following methods. A. #define, #undef. They are preprocessor macro definitions. B. Const keyword, for the constant. C. enum keyword for the enumerator. Example 1. #define, imax, 20. Example 2. Const, int, imax equals 20. Example 3. Enum, within curly brace, imax equals 20. Hence from above examples, imax plus 10 will be 30. Because imax will be replaced by the number 20, as imax has been assigned the value 20. Remember that imax is a constant. So with this, we come to an end of this chapter on character sets and tokens. If you have any doubts, please let me know. The next chapter will be on operators. Until then, bye and take care.